guy has C int, so its output is also, so if this guy has C1, C2 is equal F times C1, and C int of this guy is equal to F times C int of this guy.
Yeah. Oh, okay. Well, well, I thought you meant like.
All right, let's get started. Good morning, everyone, and welcome to week 5 of E141. So I have a long list of announcements today. First, the activities in the next week will fully revolve around midterm, and a couple important changes. There will be no homework uh, posted this week, so no homework due next week. There will be no labs next week. Lab number 4 is going on this week, and we'll make a little break next week because of midterm. So there will be no lecture next Thursday, and we will have a midterm in the afternoon, and we'll find a larger room. I'll announce that next in the next class when I figure out the exact location. Uh, Homework 4 is due this Thursday, and I understand you had a lot of work in the first 2 homeworks 2 and 3, but you shouldn't be worried. It's really for your own benefit, and we are really gentle on grading, so we really emphasize and stress on methodology rather than numerical answers. As a result, you can see some of the homework 2 stats here that basically almost everybody in the class had more than 80% of score, which is really great. And homeworks will be only 10% of your grade, so it's really important that you learn the stuff. That will be reflected in your exams and projects and so on. So don't worry about homeworks. It's important that you understand the concepts and do the work. So more information about midterm 1. It will cover all the material that we discussed so far, and including today's lecture. So it'll be everything up to this point plus CMOS scaling. So that required readings for the midterm will be chapter 1 and chapter 2 partially, that talks about some of the aspects of manufacturing process. You basically just read the material that we covered in the class. Then chapter 3 also not entirely, because we didn't go into too much detail about diodes and stuff like that. So basically just all the stuff that we talked about in the class, certainly MOS transistor and everything related to that. And chapter 5, inverter, VTCs, noise margins, performance, power, and so on. And that will hopefully give you enough time to digest the material and get well prepared. The exam will be open book, open notes. You can bring as much material as you like, as you need. And we will try to, of course, make a fair exam. And a rule of thumb is if instructor and the TAs can solve all the problems in about half an hour, that's a fair exam for you to do in hour and a half. So you'll have plenty of time to think, but the problems will not be really straightforward, that you can just basically copy down the equations from the book and apply them. You really need to understand where is all this stuff coming from and be able to apply your knowledge in the right way. So when you get a problem, don't hurry to try to solve it right away. Just give it a little bit of time, think about it, and when you're sure that you have correct approach and methodology, all you need to do is basically just write the answer. It will not be really exam that will test your mathematical and analytical skills. Won't be too much calculations, but it'll be really sort of understanding the concepts type of exams. You'll have plenty of time, and don't worry about the time pressure. So we posted a couple of past midterms on the web. There is a link from the main page. If you go to the class website, you will find a link to previous midterms. There is 5 exams there. One has the solutions, and just to get you the feeling of the way it looks like, and then you will have another 4 exams that you can solve yourself. So I encourage you to take a look at those problems as early as you can, because next Tuesday I will hold a review session with the TAs. It will be 6:30 till 8:30 in the afternoon to make sure that it doesn't overlap with your other activities or arrangements, so you kind of moved it toward the end of the day. And what we're going to do in this review session is 2 things. One is I will first ask you if you have any questions, if you need any clarifications, if you haven't understood some parts of the lecture material, then I'll be happy to explain it over again if you just need to make sure that you understood it correctly. So I'll kind of sort out all the requests and then go over really important concepts and help you get on the same page. Then also in the second part, we will get to solve one of the practice midterms. So from the problems, I will ask you which one would you like me to solve, and then we'll go through the solutions and sort of walk through the exam solving process. And that's the purpose of that review session. And next week, so no homework, no labs, but there will be regular office hours and discussion sessions. And this week there are a couple interesting presentations. If you missed the IC seminar yesterday, there was a talk about sort of microprobing and microsurgery of real life products, sort of verification type of ideas that you do in practice when you get the product that you invested a lot of money in, and then some pieces don't just really comply with the intended specifications, so you have to sort of do a little bit of fixing. So you can basically trim down the transistors, you can remove wires, you can rewire things and so on. So in general, IC seminar is occurring on Mondays, 4 p.m. 521 Corey, if you're interested. That's a really good source of information, and you can hear a lot of interesting presentations. And there is the seminar also coming up tomorrow at 4 p.m. in HP Auditorium over in Soda Hall at 4 p.m. That should be a great colloquium about multi-core systems. And the talk will be given by Mike Rosenfield, who is the director of VLSI systems at IBM Research in Yorktown. So if you have time, it will be a really good talk from the digital circuit design perspective to attend. Okay, so last time we talked about buffer sizing and power dissipation, and today what we're going to do is we are going to look at the Moore's law again and apply the knowledge that we acquired in the meantime between the first lecture when we introduced Moore's law and today, and sort of develop some first-hand models, first-order models for hand analysis, sort of to make a prediction. So where is this all coming from, and where it's going to go looking into the future. But let me first finish with buffer sizing stuff that we discussed last time. And so what we concluded, if you have a buffer chain problem and you have to drive certain load capacitance, let's say you have 16 over here, and then you assume that your input is fixed at 1, then the question is, what is the optimum sizing factor of the gates in the chain such that you minimize your propagation delay? So we call this sizing factor F. That is the ratio of the input gate capacitance of the next gate in the chain to the input gate capacitance of the previous gate in the chain. And we derive this really nice and simple formula that relates the gate parameters to the propagation delay. So we say that it is equal to TP naught plus 1 times 1 plus f over gamma. It was really nice and simple formula when you have that the TP naught is simply equal to the intrinsic propagation delay of your gate that is not loaded with the output capacitance, and it was independent on the gate size. It was purely topology and technology dependent parameter. So we kind of put it in front and scale everything to that parameter for a given technology. And then we have this parameter gamma, which was equal to the ratio of the gate and intrinsic capacitance for an inverter. And we said that that parameter gamma is usually around 1, and it can be abstracted away in most cases. Now, the question was, if you have a chain of gates, what should this sizing factor be such that I minimize propagation delay? And then we derived by differentiating this formula, dTp over df, setting to 0, we found out that this optimal sizing factor in this case was equal to the square root of the load capacitance to the input capacitance of the first stage. And this was the square root of the capital F. This was called F, in this case, was equal to 16. So then we said F is equal to 4. That's the optimum factor that minimizes the propagation delay. Now, the question is, let's assume that we have a little bit more complicated situation here. How about the case where we have the same gate at the input, unit-sized, and then we have multiple parallel branches that all drive the same load of 16. So now let's look at this path over here and see what's going to happen. In general, you may have different loading conditions on these parallel branches, and then you will then choose, you will have to write a set of equations and choose to optimize the slowest path first and then figure out the rest. But you basically have just a system of equations. It will be slightly more complicated, but the principle is basically the following. So you write down the expression, delay expression. So you have Tp is equal Tp naught, and we have to figure out this F factor over here for this gate. So now you have 1 plus the total load capacitance looking into this node is equal to 4 times F, because you have 4 identical gates going on in parallel. So you have 4 times F plus Tp naught from the second stage. It's equal 1 plus, so you have this capital F divided by F, the size of this previous stage, sizing factor of the previous stage. Now, when you differentiate this, do the same thing, dTp over dF is equal to 0. That gives you, so Tp naught goes away because it's a constant, so you have 4 minus F over F squared is equal to 0, and then you have that your optimal F is square root of F over 4. So F is 16, so this is square root of 4. So now remember, in the previous case you had F is equal to 4. Now you have a square root of 4. So basically your sizing factor for equal delay when you have these parallel paths is getting reduced. What this means is that to make equal propagation delay in both stages, you basically have to have a smaller sizing factor due to this branching, and we'll get back to that in much more detail when we talk about logical effort in the introduced concept of branching. But for just a quick analysis here, what goes on here is that you have also longer delay, because you had in the previous case just 1 plus f, so you had 1 plus 4. Now you have 1 plus 4 times square root of 4, which makes sense because of the smaller upsizing factor. Each of the stages has to carry more effort. It has longer delay, and therefore the resulting delay is longer because of this extra side load, and which does make sense, right? Because you have to spend more uh, effort in driving all these side loads with your gate, and that results in the higher propagation delay. Now there is also another case that you can consider, and I'll leave this for exercise for yourselves. So you have basically the same type of configuration, and now we have a side load. So let's assume that this is, for example, due to wires or something, that you have a side load of some fixed capacitance, and now you have to figure out your F factor. And as I mentioned when I talked briefly about the midterm, don't really try to use equations that are just out of the book, like square root. If you, for example, say, well, my f is now square root of 16 over 1, because that you really need to understand where it's derived from. So if I ask you, for example, in this case, if the problem is, let's minimize propagation delay, what you're going to do? The correct methodology, you just write down propagation delay expression. So you have for the first stage, you have 1 plus, and then you have basically f plus 4. That is the load on looking into this node. And then you have the second stage, TP naught 1 plus 16 divided by the input capacitance of the driving gate, 16 divided by f. And then when you do dTP over the f is equal to 0, then you figure out your optimal f and you're done, right? Okay. And you'll find a couple of similar problems in previous midterms. So make sure you understand where the results are coming from, and make sure that you develop a methodology that starts from the correct set of equations. Okay. Any questions? Okay, good. So let's now continue going back to slides, please. Thank you. So now let's continue with CMOS scaling and understand the impact of technology scaling. And then later on, toward the end of the class, probably like 10 or 15 minutes, I will spend some time discussing some of the common questions you had about homework number 3, and then make sure that we are all on the same page, make clarifications so that you understand clearly what were you asked to do in the homework. Okay, so technology scaling. So the main goal of technology scaling is basically, from the economic perspective, is to make things cheaper and more affordable to a user. So basically, underlying Moore's law, and that basically observed this tremendous progress and quantified in terms of complexity, number of devices that increase basically every due to feature size compactions, that we have enormous capability to increase the functionality in the same die area, or we can basically implement the same functionality in a much smaller area due to these compactions. So that is basically the fundamental principle, that due to advances in manufacturing technology, we are able to provide our transistors in much smaller form factor, and that enables us to do a number of things. So we can basically sell more functions per chip for the same money, because in the same die area now we are able to integrate much more functionality. Or equivalently, if you want to build the same products, we can do it cheaper because it requires less area. And the reason why this was possible is because due to compactions, the price of a transistor was reduced, and it's being in place for the past 40 years, that continuous reduction in the feature size and the price. But you also want to have other parameters from your design. You want also your designs to be faster, smaller, lower power. And now that we understand the concept of speed in digital circuits, and also the power, we will see later on in this lecture how we can basically derive where is this all going looking forward. So the technology scaling happens every about 2 to 3 years. One generation spans about 2 to 3 years in time. And what's really going on is basically reduction in feature size. And there will be other parameters that we will also discuss. So basically what this leads to is reduction in gate delay by 30%, the same factor by which feature size is reduced, and that's going to become clear in a moment, which results in operating frequency increase by 43%. It's actually going to be more than that. It's not going to be a factor 1.43, but rather factor of 2, and we'll discuss that also. And it doubles transistor density, and energy per transition reduces by 65%, and die size is upsized by 14% per generation. Now let's assume that we have, going to the overhead, that we have a technology that is available to us today. And what we really want to do in technology scaling, let's assume that we want to scale dimensions of our device by a scaling factor S. And there is number of parameters. There is channel length, there is channel width, and then it is also going into the third dimension. There is T-ox, the oxide thickness, and there is also other parameters that affect our quality measures, such as performance and propagation delay that we discussed, and it's basically voltage, supply voltage, threshold voltage. So how about reducing those numbers by the same factor as well? And so basically there is a number of scenarios in which we can look the scaling process. And let me just see what we are going to do over here. So okay, let's go back to slides for a second, and we'll get back to this. So basically, this is the scaling concepts that we are going to talk about, and this is the roadmap for technology scaling. This little chart here shows basically technology generations that are available to us in a certain period of time. So for example, in today's technologies, we are working with 100 nanometer, basically 90 nanometer technologies, and also playing with 65 and even 45 nanometer nodes. So what this tells you basically, let's say in 95, we first introduced 350 nanometer products in 350 nanometer technology. And then we typically need about 5 years to phase out a technology. Once technology is fully developed and becomes commercially feasible, you want to make it, take advantage of that and basically just produce as many products as you can. And for example, then in 99, you first introduce 118 nanometer technology, and you keep using that technology for the other 5 years in the future. And today, for example, quarter micron technologies has been already phased out. And you can also see these funny numbers like -1, 2, 3, and 4. And what this means is basically just a development cycle. You need a certain number of years to develop your technology for the full manufacturing capability, and then you use it for a certain period of time in the future. And there is also, in addition to that, there is also this blue stuff that's basically planning ahead and developing the next technology generation for the future use. And today, as I mentioned, we are basically using mostly 130 micron product technologies we will see in commercial products, but more 90 nanometer technology products are also entering the market and will be in widespread use for the next about 5 years. And then we are slowly moving to the 65 nanometer technology. If you're doing your research projects, you may end up working with these technology nodes like 90 or even 65 for more advanced processes. So there is some time overlap of semiconductor technology generations. And normally, with each generation, when you scale designs to each generation, basically, the first time you make it commercially available, you also have these changes in microarchitectures that we discussed, like in microprocessors, and then later on, for the couple technology generations looking forward, you have just the shrinks and compactions until you introduce a new design. So how is this really all happening? Because it seems like pretty complicated process, and it actually is, because there is a lot of parameters that you need to consider. And there is this SIA association, so it's a Semiconductor Industry Association. That's basically a consortium of all the companies around the world that are meeting regularly and trying to decide about the roadmap and how the technology is going to proceed in the future. And what they created is basically this International Technology Roadmap for Semiconductors, or ITRS. And here's the data from the 2002, and they keep revising this roadmap every year, basically. And uh, so basically, this was first called NTRS, so National Technology Roadmap for Semiconductors, when mostly U.S. companies were driving the progress in technology. As you know, Intel is basically defined the Moore's law, and like other companies like Motorola, IBM. But then, with more like widespread use around the world of technology development, many other companies joined, like Philips, ST Microelectronics, TSMC, and so on. So it's basically now SIA is grouping members from all the world regions, like Korea, Japan, Europe, US, and so on. And these people are doing crystal ball gazing, so looking into the future and sort of trying to give a forecast of what's going to happen. And they take into account a bunch of parameters, mainly basically applications that are main drivers for the technology use. And then based on those, they decide about the future trends for the technology. And normally this ITRS roadmap gives you information about the next 15 years of technology development, and it's getting constantly revised. Numbers change over time based on many other parameters that occur in the meantime. But what we can see from this table, basically, if you look at various parameters over time, so for example, the density of memory is going to improve with each technology generation. So you basically have the minimum DRAM pitch that's going to be improved with introduction of each successive technology node that occurs every about 3 years. So we have 130, 80, 180, 65, 45, and going all the way to 22 nanometer channels in 2016. So now what's this going to mean in the number of transistors per chip, logic transistor per chip? It's going to increase rapidly. So just for reference, Pentium 4 processor had about 125 million transistors, and where is this going to go into the future is going to be a 3 billion transistors by 2016. And what we're going to do with these 3 billion transistors, no one really has a clue yet, but what's going to happen likely, and if you go to tomorrow's talk, you will get probably a good glimpse of that, is probably multi-processor systems. You will have, instead of like one local powerful computational core, you will be mostly having like interconnected array of processing elements that are able to do a lot of jobs and provide you a lot of processing power. And so now going to shrinking technology, you will also have to add more wiring levels. So in quarter micron technology that we used in class, we have only 5 metal layers, but now going to today in 90 nanometer, we have 7 or 8 metal layers, and you will basically, due to increased complexity, you will have to add more and more levels for signal routing to be able to connect all the signals at globally. And now, as I said, in order to create this forecast, you have to consider a bunch of factors and bunch of basically applications that are driving the semiconductor industry. Microprocessors have been mainstream for technology scaling, and then later, lately, in the 90s, basically we had proliferation of portable devices and cell phones. Cell phones are the major industry driver for low power and portable electronics. And that's the reason why these technology roadmaps today now have two scaling trends, basically. They have a high performance uh, scaling for microprocessors, and they have a low power scaling for these portable devices, because those are two major applications for semiconductor industry. And then basically for the high performance and gates, we have basically the applications will be mainstream desktop computers or servers, really like large scale supercomputers and so on. And then what's the main difference is basically for these kind of devices, all you care about is basically performance, the amount of processing power that you can deliver over time. And this performance is quantified in terms of local clock. And now you see that today processors have about 3 gigahertz of clock operation. And where is this going to lead to? If we keep business as usual and continue with the scaling trend, it's going to end up in about 30 gigahertz of operation. And that's local clock, basically. So distributing this high frequency clock globally over a large die, it's going to be almost impossible. It's going to be a real problem. So basically, you will have all of these machines working in isolation and basically performing some operations locally, and then you will have like a more global communication between all of these processing modules that occurs less frequently, because all the computation will be sort of distributed and centralized across these processing nodes, and then you will have to sort of exchange the results of computation at a less frequent rate than the local clock. And what this going to lead into is basically huge increase in power. So you have 300 watts of power in your processors by 2016, according to this forecast. Now, for portable devices, there is no way you can sustain these power levels. So you basically have to carry maybe like 50 pounds of batteries in your bag and have a little phone that you can use to talk. And basically, as I said, predominantly mobile phone industry has been defining this low power scaling trend, and the main requirement there is to keep the power constant. And the reason why you want to keep the power constant is because you have to you want to keep the battery size the same, because the battery energy capacity of the battery hasn't improved much over the years, and basically until that problem gets solved, we have to stick with constant power. Now, the good news for us is basically once we are able to sort of integrate the functionality of a phone on a chip for a given battery capacity, then we are able to provide some basic functions like voice and so on. And now with the technology scaling, the pure benefit of technology scaling, that you can integrate more functions on the same die, basically for the same cost and same power consumption. And therefore you can add more of these like data-centric types of applications where you can handle SMS messages. You can do then later on even taking still photographs with your camera, and maybe playing some video streams and so on. So that is what's going to be enabled by future technology scaling. And the power consumption was limited by this basically 3-watt power wall that is defined by these mobile devices. And then what's going to be the difference in scaling the supply voltage over here for the high performance and low power devices is basically you see that surprisingly that supply voltage will get more aggressively scaled as we go forward in high performance scenario than in the low power scenario. And this is basically just a prediction going from today's values of about 1 volt for 90 nanometer. This is going to end up in zero point 0.4 volts for high performance and about zero point 0.6 volts for low power. And the main reason for this is basically leakage power. So basically, if you keep scaling your VDD and VT very aggressively, then the problem becomes your leakage power. And if you look, for example, into typical applications for your portable devices, you basically have your phones that even if you are really uh, like a prime user and then you really use your phone a lot, like what's the plan that you can get? Maybe like 3,000 minutes per month, and if you scale that by the amount of time, if you really like talk for the 3,000 minutes for a month, that's going to be maybe 10% of, if you scale that by the 24-hour day, it's going to be maybe 10% of activity. And then during that 10% activity period, you have your underlying circuits that may maybe switch internally about 10% themselves because of the switching activity that gets reduced when you perform some logic functions. And what's this leading to is basically that the overall, even like in the worst case scenario, if you're really using your phone all the time, you maybe have the total activity of about 1% in average. And the rest, you are idling and you're consuming leakage, standby power. So that's why leakage is really, really important in this case, that you're trying to minimize the leakage. And in order to sustain the performance, you would have to basically operate with higher supply voltage, but also you have higher threshold voltage to be able to work with this standby power consumption problem. And in the high performance basically cases, you want to deliver as much computation as possible over a period of time. Leakage will be a problem there as well, but you're basically, as far as you are plugged into the wall and your chips are not melting for power density reasons, you're fine. You'll just pay higher electricity bill and you'll still do your job very efficiently. Okay. So this graph is really interesting. It's kind of you have to be in a special mindset to create this kind of graph, but it sort of includes all the factors that we just discussed. So basically, you have all the factors here, number of logic gates and so on, technology generations over time, technology nodes. But really, what I want to emphasize in this graph, that's the only reason why I put it in the lecture notes, is basically to sort of emphasize the point that all these predictions really changed over time. So let's look at the 1994 technology roadmap predictions for the minimum feature side. So that basically was also like all these lines are basically going on on a these are straight lines, like linear trend when you consider year of introduction for new technologies. And then what happened is basically in 1997 is that we got basically sort of ahead of time. So we were able to really scale our technology faster than we originally thought. And that really happened, this huge acceleration happened in the 90s. So basically in the 90s, where all the people were so excited about these new mobile devices and everything, they were really determined to make this scaling happen, and they were really working hard to show they can make phones and all these cool devices so that they can basically put them onto market. And they were really eager to sort of deliver new functionalities and scale technologies in a really rapid way to enable all this to happen. And then in 1998 and 1999, this trend also got sort of accelerated. And basically now, if you plot the 2002 trend line, it's going to get back to the old trend. Now, basically, people said, well, we figured it out. Now it's no longer fun. Let's just keep scaling the way we used to do in the 90s. So now, you can look at this technology scaling from a number of basically quality metrics. And basically, underlying principle is the Moore's law, the minimum feature size scaling that is going on at about 2 times every 5 years, or a factor of 30% every 0.7 factor every technology generation. So today, for just entering the commercial widespread use is 90 nanometer technology, and this trend has been in place for 40 years, which is really amazing that you're able to sustain some exponential law for a long period of time. And then looking forward until at least year 2010, we will have the same trend going on, and then we will see what will happen afterwards. Uh, then another metric you can evaluate this technology scaling is basically if you look at the number of components per chip, and what's shown here is the number of components, transistors that are used in the processor, and also number of memory transistors over here in blue. And that's been also going on at really spectacular rate following this exponential trend over time. Um, then another factor is the speed. Basically, the speed is normally calibrated with the microprocessor clock frequency. And what's been going on is that just due to technology advancement, now we are not talking about any like design cleverness, microarchitectures and so on, but just what the pure technology scaling can deliver to us is if you keep scaling your dimensions 30% every technology generation, then due to the reasons that you will understand in a moment, your propagation delay of a gate will also decrease by 30% per year. Now, that's 0.7 factor. Frequency is 1 over propagation delay. 1 over 0.7 is 1.43, so your frequency increases by 43%. And that's been the trend for the past 40 plus years. Now, another very important factor is the power consumption. That is what is really limiting the technology scaling today. And this is a plot of various processors, various, a lot of things going on here. It's basically processors, classical microprocessors and the DSP processors and so on. If you plot this data over, so basically each design corresponds to one dot in this graph, and this is the data collected from the International Solid State Circuits Conference, that is the prime conference for circuit designers to show their work. And you can see basically there is a lot of points here, but what I would like to emphasize from this graph is that you see that the power dissipation has been going up rapidly, like 4 times every 3 years. And then that's been the trend all the way up to about 90s, where we had basically two things going on. We had this like a decrease in power consumption on in one direction, and also we had the leveling off of the power scaling trend as we go forward. And now the reason why all this happened is basically all the way up to the 90s, you had constant voltage scaling. So you basically didn't scale your voltage, but you just scaled your transistor dimensions. That would result in much higher power than if you just scale the voltages as well. So what happened in the 90s, basically, people started doing voltage scaling, and we will discuss the scaling scenarios in a minute. What happened here is basically the leveling off for the power consumption was caused by also simultaneous scaling of both your dimensions and also voltages. And the reason why you want to scale the voltage, what happened is velocity saturation. So you basically now have the case where you can no longer get a quadratic benefit in performance from your device, but you basically have velocity saturation. No matter how much you increase your drain to source voltage, meaning your supply voltage, for the technology you still have the same speed. Your velocity saturation limited and game over. That's the end of the story. So that's why you have to basically keep scaling supply voltage as well. And that's shown in this trend over here. Another trend that's going on, as I also mentioned in the 90s, for this acceleration of mobile devices, basically you had more and more mobile computing going on, and these devices were really limited by the amount of power they can consume. So then the power had to drop down. So that sort of explains this scattering all over the place that's been happening in over a period of time of about 20 years, from the 80s till about 2000. And there is also another factor that's really important, because power density, that is the power density. So that's the power consumption per unit area. How much power you can dissipate per millimeter square. And that ultimately defines your thermal, basically dissipation, power dissipation, and your density and the capability at which you can basically take that power out of a chip. So that basically it means heat sink design for desktop machines, and it means basically power limit for the portable devices. So no wonder you have basically, due to power limits, you have a fixed power in your mobile device, but there is also this another parameter that is ergonomic limit from a user perspective, that you can only sustain certain temperature. Imagine taking a phone that is, I don't know, 150 degrees and then put it on your head. It's not going to be really comfortable for you to speak onto that device. And that's basically another reason. And then basically for the reasons of constant voltage scaling, we had uh, basically improvement in the density of our devices, but then the voltage didn't decrease. So that basically led to constant increase in the power density. Eventually it became a problem, and then when we started scaling voltages, it leveled off. Okay, now let's understand how we can really capture the impact of all of these parameters and sort of understand various modeling principles, how we can derive some simple models that we are able to predict these trends. And that's not going to be too hard, basically. So now let's understand what's been going on over time and sort of derive several models for scaling and to be able to capture the effects that happened with time. So let's now start, go back to the slides, the drawing that I started to put together ahead of time. So basically you had your design, and let's now assume the ideal case where I want to scale up all parameters at once. And this full scaling is basically motivated by the idea to preserve electric field. So if you keep scaling your voltage and your channel length by the same factor, you have voltage over channel length. It's basically staying the constant, and that's basically the constant electric field. You want to make your devices work in the same sort of environment as it worked in the previous technology, and that is the full scaling model. This is ideal model, and we will understand its shortcomings in a second. But let's now for exercise, now that we know about models for various parameters, see what's going to happen if you just keep scaling all the parameters. So let's consider scaling dimensions W, L, and T aux, and over time, let's assume that S is greater than 1. So let's assume that over time we have that W, L, and T aux for the next technology generation is now going to be 1 over S from the previous generation, right? Due to the compactions in manufacturing process. So now voltages, let's assume that we also scale down the voltages, both threshold and supply voltage at the same rate, to be able to sustain the performance on the roadmap trend. And now, so that's the basic stuff that you know. Those are your assumptions. Now, so let's see what is the impact of this scaling on various parameters. How about area? So that's the number of devices you can integrate on the same die. So area is proportional to W and L. So that's your transistor. So basically now you have that your area is quadratically reduced with scaling of technology. So you have a lot of benefit there. So now I would like to know about the speed. So and the speed is defined basically by two parameters. You have your capacitance and equivalent resistance. That's the propagation delay. So my capacitance is basically dependent upon this gate capacitance or oxide capacitance. Now I know that oxide capacitance is inversely related to this T aux. So if T aux goes down, then my area goes, then my capacitance per unit area goes up by a factor of S. Right? Same happens for the load capacitance. Basically, the load capacitance is, so this is just the capacitance per unit area. So the load capacitance is proportional to the capacitance per unit area times the area. And then you end up with the scaling factor 1 over S. So your load capacitance, the capacitance that you need to drive, decreases with a factor of 1 over S. Now, what happens with the average current? So the current is proportional to C aux W over L, and voltage squared. Now you really have over here basically you have VDD minus VT squared, but since VDD and VT scale the same way, you can basically approximate this and say that's the voltage, but it's the same way the VDD scales, right? So W and L cancel out, so you have now let's see, C aux is S, and then you have 1 over S squared for the VDD, and that gives you 1 over S. So now the propagation delay. Propagation delay is proportional to the load capacitance, voltage swing, and average current. This is basically your equivalent resistance. So this is now gives you CL is 1 over S times the voltage goes 1 over S, and your average current also goes 1 over S. So propagation delay ends up improving with this factor 1 over S. Now, very important observation here. The improvement in propagation delay only came because of improvement in load capacitance, right? Your equivalent resistance was constant. So only reason why you had faster transistors is because your capacitance reduced. Now let's look at the more factors. So how about power consumption? So we derived in the last class that the switching component of power, which is the dominant power in digital circuits today, and that's the only useful component of power, is proportional to the CL, and then you have VDD squared, and then you have the frequency of operation, and the frequency of operation is inversely proportional to this propagation delay. So what this gives you is basically the capacitance. Now we have 1 over S, VDD squared is 1 over S squared, and then we have times, no, VDD squared goes, let's see, CL is S times 1 over S squared. CL is, let's see, 1 over S. Let's do this again. So 1 over S. So VDD squared is 1 over S squared, and 1 over TP is S. Right. Okay. So that gives you power equal to 1 over S squared. Now, interesting thing is that if you keep scaling everything all together, your voltages and your dimensions, if you look at this area over here, and you look at the power, so basically power per unit area stays constant. So that's the reason why we had in fixed voltage scaling increase in power density, because we didn't scale the voltage, but we just scaled the area. And now this basically explains, if you look at so now capacitance is further proportional to, so it's epsilon over T aux, and this parameter is basically, so let's get back to that later, not to confuse you now. So that's basically the general scaling trend that you have. The problem with this trend is basically when you enter this model is ideal when you assume that everything scales by the same factor, and then later on we will come to that basically due to the velocity saturation effects, and that you have to basically scale your voltages and your dimensions by different factors for the speed reasons and also for the power reasons. So let's now look at the scaling. Go back to slides. So now let's look at several of these scaling scenarios. Basically, if we let's consider first long channel devices, because those are the type of devices that we had in the past that explained basically the technology progress when we had long channel and we had fixed voltage scaling. So we already did exercise for this scaling model, basically starting from these parameters W, L, T, aux, VDD, and VT, and then we derived area, capacitance, intrinsic propagation delay, and the average power. And this is the idealistic scaling model. In reality, what happened is basically this fixed voltage scaling over time, all the way up till until up in the 90s. And then you had from this fixed voltage scaling, then you had basically that your power uh, would increase, and you basically had that your area of a device would also improve quadratically. So now when you multiply the two, you basically have that your power per unit area would go up as a scaling factor to the power 3. Now if you go back to this slide, that exactly explains this scaling trend over here. So you had your density that goes up with a scaling factor k cubed. And apparently this caused a lot of problems for the power perspective, and that's the reason why people started scaling voltages. Now, uh, the question is, what would be the most appropriate way to scale your supply voltages, given that you have your velocity saturation in play? And so basically, we understand that fixed voltage scaling is no longer valid because of this power density problems. And the full scaling is also idealistic, so that is not applicable. And now we know that basically when your velocity is saturated, that the increases in voltage are no longer leading to the benefit in performance. And that is basically just a first order approximation. When you keep increasing voltage, you really have the short channel effects and channel length modulation, and then your performance does increase a bit, but this is really just a secondary effect. And what we're really concerned here is to understand the primary reasons why the scaling has been going on as it has been. And now if you look, for example, from the scaling of zero point 0.5 micron technology over to 0.13 micron technology, you will see basically the scaling of voltage from 5 volts to 1.5 volts. That is basically at a less aggressive rate than the scaling of technology. And the reason why in the first place people used fixed voltage scaling is basically purely due to legacy reasons, because you had some standards for your voltage levels, and then when you introduce the new technology generations, you would be able to plug the same component in the previous environment, in the previous system. And now, even if you look today, that's basically legacy trend that's present in industry even today. For example, if you're looking for commercial components, off-the-shelf components from DigiKey or whatever supplier, then you will see basically that you can today pretty much find everything that is compatible with 5 volt standards, 3.3 and 2.5. Maybe 1.8. Getting down to 1.2 volts or 1 volts, it's still going to take some time to get there. But basically, with realization of this power problem, people were forced to scale the supply voltages down and adopt new standards for supply voltages. And that's why you had basically 5 volts for a very long period of time, 3.3, 2.5, and so on. Now the question is, if you have velocity saturation problem, the question is, why do you keep supply voltage that high? Because basically when you increase voltage beyond the velocity saturation point, then you have to a first order no longer benefiting performance. And the simple reason, there is actually two reasons for that. One is because there is other voltages that are dependent on the material structure, such that built-in potential for the junction potential for the NP junction. And also another factor is basically that if you keep scaling voltages at a very low voltage levels, you have two dominant effects. One is leakage power, and another is variations. And that's the reason why supply voltage hasn't been scaling at the same progress as our dimensions. Now let's look at a more realistic scaling scenario for short channel devices. So basically, from the story that we already presented, we had these different scaling factors. So basically, We had fixed voltage scaling, which was good way back in the past. We had this full scaling that basically is not good from the purpose of idea of arbitrarily scaling supply voltages, because that has its own limitations for variation reasons and also for leakage power reasons. So we had to adopt basically this general scaling model when we assume that, let's say that all the dimensions, horizontal and vertical, scale by the same factor S. And let's assume that the voltages scale by the same factor, but other factor U. And to keep the performance on track, we have to scale both VDD and VT by the same factor. And now, if you look at this table, a couple observations. So basically, R on is always constant. So all the performance improvements that you get from any of these models come from improvement in your capacitance, your gate capacitance that always scales with 1 over S. Now, when you put basically U, when you set U is equal to 1, when you get the fixed voltage scaling, and when you set U is equal to S, then you get the full scaling. So basically, this general scaling model is important to understand because it's general enough that you can go between full scaling and fixed voltage scaling. And what this also tells you is that now the power density that is clearly the problem is now somewhere in between the full scaling, which is the ideal scaling scenario, and the fixed voltage scaling. And this is the model that you really need to understand. That's the important model that is underlying development of modern technologies. Any questions about scaling? Okay, so now let's see how this plays out in real life, and I'll repeat a couple slides from the introductory lecture. So basically, if you look at the number of transistors on a logarithmic scale on the vertical axis versus year of introduction of various microprocessor families, then we can see that basically this model is validated in practice, that you have about 2 times improvement every 2 years, or every technology generation, number of transistors on a die doubles, because we are able to integrate the same in the same area 2 times more functionality for roughly the same cost. Now, what is this going to cause for the power consumption is also an exponential increase. And that's the reason why about the year 2000, which is when this prediction was made, we basically had to start worrying about the power consumption and scale voltages in a different way than we did in the past, and also worry about this excessive leakage problem that started to appear. And microprocessor performance, if you look just at the pure technology scaling model, going from 1 micron and scaling all the way over time to 0.18 micron, then you can see that over this 1, 2, 3, 4, 5, 6 technology generations, you have about 2x improvement for each generation. So it's about 12, 13x improvement in performance just due to technology scaling. Now it happens in real life that you have additional 6x improvement in performance, and the reason is that we discussed in the introductory lecture is basically that you have more pipelines, more pipeline stages. So you have basically you are shrinking your logic depth between the pipeline stages, so that gives you the ability to increase the clock frequency, and also you are using more clever circuit design ideas. For example, you employ dynamic gates that are faster than the static gates, and over time people understand technology and come up with various clever ideas at all levels of design abstraction to sort of make this happen and go at even faster pace than it was originally intended to go. Now, where is this all leading to? By 2010, if you just keep doing everything as usual, you will have, in terms of performance, machines that go with 1 tera instructions per second and running at 30 gigahertz clocks. We would be able to integrate about 2 to 3 billion transistors on a single die. That would be 40 millimeters on a side. And the power will be in the kilowatt range if we keep doing this as we did in the past, but it's not really going to happen. Something will change by then. And the leakage power is becoming a really important factor over here. But we are really getting more power conscious looking forward, because traditionally computing devices will be more sort of like a communication devices. So connectivity will be required from devices that were traditionally used for computing, such as laptops and also mobile phones and other PDAs, other portable devices will become platforms that will drive computing, because they will be able to do much more of a computing. And if you just compare, for example, some modern PDAs from 2005, their capability in terms computing terms, in terms of clock frequency and the amount of memory, is comparable to that of 2000 generation of Intel Pentium processors. So you have levels of clock rate of about 500 megahertz readily available, and 128 megabytes of RAM memory in these PDAs. That kind of catching up with the computing capabilities. And the interesting questions obviously is, what will cause this model to break? When will it break? There is a lot of research now going on in these nanotechnologies, carbon nanotubes, alternative devices that are promising in terms of power consumption, and that's basically the reason why we kept changing technologies from bipolar to CMOS, and now we will see what will come after year 2010, when we have a lot of these like opportunities being researched at this point in time. And obviously the valid question is, will the model gradually slow down for power and power density purposes? And the main problems are power leakage and process variation when you go to small feature sizes. And so this basically completes all the material that you need to prepare for your midterm. Next time we will go into wires, but now let me go back to what I promised in the beginning of a class and make clarifications about homework number 3, to just put you all on the same page and make sure that it is well understood. So let's now go switch the camera to the overhead, and let's analyze problem number 1, because that was the most, I think, demanding and problem where you had most questions. So we basically had this NMOS structure where we had VDD over here, we have input voltage, and then we had this extra side load, and we had V out. And then the question was to find the VOL, VOH, VM parameters. And this problem was further simplified by the assumption that all these transistors are basically long channel sort of devices, that you just ignore short channel effects and make sure that instead of velocity saturation, you do classical saturation. So in that regard, this problem was really simplified version of what you could have gotten in your homework. But I'm glad that you had a lot of questions about this problem, and then later on in the solutions you sort of discovered some inconsistencies, which means that you understood the problem, right? So that's good. So let me just now walk through this again and make sure that all the points are taken and that you understand what's going on. So now what we need to do is actually analyze the behavior of this circuit and find VOH and VOL parameters first. A couple observations. You see this diode connected transistor. That simplifies things a lot, because you're now VDS is equal to VGS. Therefore, that device is always in saturation, because you have this extra side load over here. So that simplifies a lot. So now the question is, what happens with this device M2 for VOH and VOL analysis purposes? So now let's start with calculation of VOH. And for that purpose, it's valid to assume that my VOL is going to be something that is less than threshold of this device. Let's say my VOH and VOL are not really going to be at VDD and 0 because this is a little tricky configuration here because I have the side load, and then for example for VOH, if I assume this is turned off, then I have this voltage divider, so VOL is going to be higher. But let me assume that VOL for the first approximation is sufficiently low that I can assume that my M2 is cut off. So let's make an assumption that V in is less than VT0 of this M2. And in that case, our V out will be equal to VOH. So now we simply have to equate the currents, assuming that M2 is cut off in transistor M1 and this resistor R load. So we have IM1, assuming saturation region is equal Kn over 2 times W over L times now the VDD minus VOH, that is your VGS, minus VT, and my VT is VT naught, minus gamma times 0.6 plus VOH, and we have another plus gamma times 0.6, and this will be squared because that's saturation region current, right? And this is body effect here. And my current in the resistor will be VOH divided by R. Okay, and now I have to make these two equal. So let's do that, and let's just first figure out some of the values over here. So you have W over L for this device that is equal to 4. Our Kn is 100 micro. VDD is 2.5. This is 0.5, and this term over here is coming to be 0.1549, and this is 100K. So now you put these two together, multiply 100K times 100, you're going to get 10 divided by 2, 5, so this factor over here is 20. So you would have, then basically you have 20 times, you sort out these terms, you get 2.1549 minus VOH minus gamma times square root of 0.6 plus VOH squared is equal to VOH. Okay, so you now take a square root of this, so square root, and you take this guy out, square root VOH. Okay, and then you have, I'll just put it here so I can continue with the derivation. So now you have basically from this expression you have VOH is equal to 21549 minus 0.2, which is your gamma, times square root 0.6 plus VOH minus 0.224, which is 1 over square root of 20 times square root of VOH. And now you use MATLAB or some other symbolic equation solver tool, and you basically plot this function. So this is f of VOH is equal to VOH, and then after you do that, you can get your result numerically, and you get first order approximation for VOH is equal to 1.5785 volts. Now, let's try to figure out, next step is to figure out VOL when you put VOH at the input and see if your initial assumption is still valid. Let's do that. So before we do that, we first need to figure out the mode of operation for our transistors. So now let's assume that this is 1.58, that's VOH, and this output is over here is VOL. So this one is always in saturation, so no question about that. And then since this one is sufficiently high, and assume that VOL is less than VT, because that's the best assumption we have so far, then that it comes that this one would be in linear regime over here. And then what you have is basically in this case you have for VOL calculation you have that your IM1 is equal to IR plus IM2. And then you have your IM1 is equal to Kn over 2 times 4, that is your W over L, times VDD minus VT naught minus VOL now minus gamma times square root of zero point 0.6 plus VOL plus gamma times square root of zero point 0.6 squared is equal to. So now you have your IR is VOL over R plus Kn times W over L for the bottom transistor is 8 times now you have VOH minus VT naught times VOL minus VOL squared over 2. And now you need to plug in this oh no, this is VOH here. V No, this is VDD. Yeah, that's correct. So now you plug in your VOH from the previous step, 1.5785, and you replace the numerical values for all of these over here. So what you get is basically you get your VOL is equal 20 times 2.1549 minus VOL minus gamma times square root of zero point 0.6 plus VOL squared, and you have minus 80 times 1.0785 times VOL minus VOL squared. And then you obtain from here, using the same methodology, you get VOL is equal to 0.58 volts. And that is now greater than VT2, VT0, which is equal to the VT of this M2 transistor. So now, since that is greater than VT, you have to refine your approximation for VOH analysis, and then you will have basically now VOH. So now this is your iteration number 2. So for VOH now I have both transistor M1 and M2 in saturation. And then you basically work with the saturation currents to get VOH is now 20 times 21549 minus VOH minus gamma times square root of zero point 0.6 plus VOH, and then you have minus from the bottom transistor 40 times, and now you have VGT squared. It's basically 0.08 squared, and this was because 80 divided by 2. And then when you solve this, you end up with VOH is equal 1.56, which is good because it's close to the previous assumption. You had 1.57, now you have 1.56, and then you plug that into this set of formulas, and then you get VOL is equal to 0.58, which is sufficiently close to the first iteration result of 0.58, and then you're done basically. That's your answer. Now the question is, what is your VM? For the VM calculation, you have, so now you basically have this situation, right? So you have, this is your 2.5 volt, this is your 0 volt. Now your VOL is equal to 0.58, and then your VOH is equal to 1.5758, whatever, 58 volts. And then this is unused region. So all the business happens between VOH and VOL now. Now the question is, where is VM? So in this case, you basically have VM is calculated when both input and output evaluate to VM. Both transistors are in saturation, so you have VM is equal to 20 times 21549 minus Vm minus gamma times 0.6 plus Vm squared minus 40 times Vm minus zero point 0.5 squared. And again, MATLAB takes you 30 seconds. You get Vm is equal 1.06 volt or so. And that is approximately equal to VOH plus VOL over 2. And then you're done. Now you can use for the first approximation, if you don't know where to start, you can use VDD and ground to compute the initial values of VOL and VOH, and that's what homework solution suggested. But you have to really go one more or a couple more iterations to get accurate answers. Question? Absolutely, yes. Calculators are allowed on the midterm, but you won't have anything of this complexity. This is just basically to make sure you really understand what's going on. Another couple remarks about homework. There was a question. You could have used the K equivalent in the calculation of your propagation delay, and that is perfectly valid. If you do that, you certainly get full credit. Basically, when you calculate the K equivalent, you will get probably about a factor of 0.65 or something like that when you calculate the K equivalent for the problem, and that is certainly good, gives you accurate prediction for the delay. And the reason why we give also full credit for the K equivalent 1 approximation is because you get a more conservative approximation for a delay, and as a designer, that is a better thing to do than to make an error on in the other direction. And I think that will be it for today. See you on Thursday.